Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today I'll be talking a little bit more about the correct version of that, the correct way of doing it. But yeah, we'll talk about validating SAT refutations, and this is joint work with Marian Hula and Warren Hunt. So today I'm going to give a bit of a motivation for why we're working on this, and then we'll introduce some SAT basics. I'll introduce what the property of redundancy is in our context, and then how to construct a proof of correctness or proof of unsatisfiability for SAT problems. And I'll present a few different types of those and explain kind of our final type, our RUP proofs, why we think they're nice or have a nice property. And then I'll present our model for a RUP proof checker in ACL2, and then a specification for it and a proof of correctness. So there's some bad news in the SAT community in that SAT solvers are buggy. And not just SAT, it's SAT and SMT and QBF. And they've been documented, these bugs have been documented in some of the literature. There are a couple of papers that use fuzzing techniques to find large number of bugs in some of the most competitive SAT, SMT, and QBF solvers. And what's funny is that even in these competitions they have for SAT or for model checking or anything like that, the competition winners may even contradict themselves between successive years of the competition. So for example, in the hardware model checking competition from 2011 and 2012, the model checker that won both of those years contradicted itself on the same problem between the 2 years. And another problem is that these errors aren't always even implementation based, right? So sometimes someone gets a good idea and they have some concept that they think is really good, and they try it out and they have no way of proving whether or not, or maybe they try to do a hand proof or something of whether it's correct or not. But the bugs can be on a conceptual level as well as an implementation level. And furthermore, one of the techniques that was introduced several years ago was claimed to be experimentally correct in the sense that it had passed millions and millions and millions of benchmarks, and still had a bug that one of the co-authors of our work, Marian Hula, found by hand, by constructing a very small hand example.
These are all for refutation.
These are for, well no, these are for SAT solvers, a bug in the SAT solver. So the even worse news is that some SAT techniques that are out there right now can't even be verified by existing proof structures that exist. So what we're trying to do then is define a proof structure that will allow us to validate all SAT techniques. So some of our solutions for this problem is we could continue to just trust SAT solvers and hope that the bugs get ironed out, and I don't think that that's a very good answer to the problem. Another answer we could have is we could try to verify the SAT solvers themselves. And this verification process would require us to have all of the major SAT solving techniques to be verified so that we could get very good performance with our verified solver, right? But this is going to have a very delicate balance between the efficiency and the ease of the verification process. So, and even more troubling is that whatever verification effort we do on some kind of verified solver is specific to that solver, right? We're now tied to this model we've written for a solver, and we can't swap out to different solvers. Or if there's a new technique that comes along that's discovered, we have to go off and implement that and verify it. So I don't think this is a very good solution either. Instead, what we're focusing on is verifying or validating the SAT solver output. And so what does this mean? It means that the SAT solver can either give an answer of SAT and provide a model, or it can give an answer of unsat. So in the SAT case, if we're given a model, we can efficiently check that that model satisfies the formula that was given to the solver. But what happens in the case of unsatisfiability? Well, we can emit a proof of unsatisfiability from the SAT solver. And we can do this with very little overhead for the solver. And then a single proof checker can validate the results from all state-of-the-art solvers. And that way, the solver we choose doesn't matter. As long as it can emit a proof, then our proof checker can validate the proof, and the solver becomes kind of a modular component in the system. And finally, the proof checker doesn't need near as many techniques, or SAT techniques, as a SAT solver would need. So here our verification effort is reduced. So what do we want from these proofs of unsatisfiability, right? Well, we've identified 5 different properties that we think are important for proofs of unsatisfiability. The first is that they should be easy to emit from a solver. So the solver shouldn't have to have significant changes to its code base to emit one of these proofs. And yeah. So and the next thing is we think the proofs should be compact. So they shouldn't take up hundreds and hundreds of gigabytes or terabytes of space on the disk, and they should be able to fit in memory so that we can efficiently check them without having to go back and forth to disk. Next, we think that our proof checker should be able to check these proofs efficiently. So ideally, we'd like the proof checker to be able to check the proofs in a time similar to the solving time. So if the solver takes 100 seconds to solve a problem that's unsatisfiable, we think our proof checker should be able to compete with the solver. Next, we want a simple checker, and this has kind of been the traditional approach, is having a simple checker that can be kind of inspected by eye and enough people agree that it's right. But I think we can go further than this. I think what we really want is we want a mechanically verified checker, proof checker. And finally, we want our proofs to be expressive. So if there's a technique out there, especially some of the ones that are used in pre-processing, that go beyond the current means, go beyond resolution and unit propagation, then we should be able to express that efficiently in our proof so that the solver or the preprocessor doesn't have to write large routines to output proof scripts. So some of the first work on this has been done on resolutions, and I think resolution proofs. And I think these are probably the most popular form of proof today right now. And unfortunately, they're very difficult to emit. These proofs usually require significant modifications to the solver, and they incur a large overhead while the solver is running to keep producing these proofs. The nice thing about resolution proofs is that they can be checked very efficiently. But again, another problem with them is that they take up large amounts of space on disk. For some of the larger benchmarks in the SAT competition, these proofs can take up terabytes of disk space. And so whenever you have a proof spread across terabytes of disk space, you end up with a large penalty going back and forth to load certain sections of the proof from disk. And there's been a lot of really nice work, though, for resolution proofs on having a verified checker. And so this increases kind of the trustworthiness of the proof checker. But again, it's based on resolution proofs and suffers the same problems. So a different type of proof that was proposed a while ago and hasn't seen a lot of attention until recently were clausal proofs, or reverse unit propagation proofs. So these proofs are extremely easy to emit. You can produce these proofs with just 8 to 12 lines or so of some of the top-end solvers, 8 to 12 lines of code modification to produce these proofs. So they're extremely easy to emit. They're extremely compact in the sense that they don't store all the information that the resolution proofs store. And they can be, but the problem is that they can't be checked efficiently. They require some amount of search on every step of the proof in order to reconstruct whether or not the clause that was added is sound. So one of our first forms of work is on DRUP. And so this is an extension of clausal proofs where now we include clause deletion information. And just adding this amount of information allows us to check these proofs efficiently. And we have a few other modifications. And this is all documented in a paper that will be at Formal Methods for Computer-Aided Design later this year. So another line of work that we've done is on establishing what we call RUP proofs. And these proofs have a more expressive proof format, and so you're allowed to capture a lot more techniques proof format. And they're based on clausal proofs, so they're easy to emit and compact, but they're still not very efficient to check. And finally, we have another work where we verified a RUP proof checker in ACL2. And so that's a little bit about what I'm going to be talking. That's what I'm going to be talking about today, is this final one. And in the future, we'd like to have a system where we can have all 5 properties. And so that's what we'll be working on later. So now let's move on to some basics of satisfiability. Yeah.
Do you think that you could make the final one efficiently check? Is it easy to have some sort of magic extra information?
Yeah.
Destroying all the other?
Right. So that's what we're working on right now. And I think it can be done. I think you can write an efficient efficient mechanically verified checker. And we're going to try to do that using ACL2. So let me back up for a minute and talk about the satisfiability problem to be clear on what we're talking about. So satisfiability says that given a Boolean formula, is there an assignment of values to Boolean variables such that the formula evaluates to true? So on the right I have a formula. You can see there's Boolean variables represented by the x1, x2, etc. And we have, this is in conjunctive normal form, meaning that we have a conjunction of disjunctions. So given a solution for this formula, so at the bottom I've got a solution, x1, not x2, x3, or not x4. Given a solution, it's very easy to validate whether or not this is a solution for the formula. So here's, now I've colored all of the Boolean variables, green or red depending on whether or not they were satisfied by this solution. And then we just have to check that each clause in this formula has one satisfying literal. But determining unsatisfiability is a bit more difficult. Now given this formula, which is unsatisfiable, how do I express to you that this formula is unsatisfiable, right? I have to somehow convince you that I've tried all possible solutions, or all possible assignments, and none of them were a solution for the formula. So first, we need to model this problem in ACL2 in order to mechanically verify a proof checker. So we do that first by establishing literals as positive and negative integers. And so here, if I had x1 before, it's now been converted to the integer 1. And if I had not x3 before, it's now been converted to the integer not 3, or negative 3. Next, we construct clauses, and we have them in our model right now as unique, non-conflicting lists of literals. So this is an implied disjunction, and when I say non-conflicting, I mean that you can't have, say, 1 and negative 1 in the same clause. We can compose formulas by having a list of clauses. And we say a tautology is a unique conflicting list of literal. So here in our model we have tautologies and clauses defined separately. And so that requires a few extra checks in our model. And so this is a tautology because it contains 1 and minus 1. And then,
Something that falls,
what's that?
the 1 and the minus 1.
So that clause would evaluate to true always, because either 1 or minus 1 would always be satisfied. Yeah, because they're an implied disjunction. And then our assignments are unique, non-conflicting lists of literals. And these are implied conjunctions. It says that 1 is true and negative 2 is true, and so on. So once we've defined our kind of data types, we can define what evaluation on those data types means. So we can negate a literal. So given a literal 1, we can negate it to obtain the literal negative 1, and so on. Next, we can evaluate a literal with respect to an assignment. So here, if I'm given a literal and an assignment, I'll return a ternary value, so either true, false, or undefined. So in the first example, the literal 1 evaluates to true with respect to the assignment because it's a member of the assignment. In the second example, the literal -1 evaluates to false with respect to the same assignment because its negation is a member of the assignment. And finally, we have it undefined if it's not a member of the assignment at all. Once we can evaluate literals, we can then evaluate clauses. So given a clause in an assignment, we'll return a ternary value again. In the first case, if any literal in the clause evaluates to true, then the whole clause will evaluate to true. And in the second example, if all of the literals in the clause evaluate to false, then the clause evaluates to false. And finally, we return undefined otherwise. Next.
So if you had the tautology with undefined stuff, it wouldn't evaluate it. It would only evaluate on clauses.
So if you had a tautology, it would always evaluate to true, just because either, well,
It would evaluate to undefined.
yeah, it could also evaluate to undefined. I think you're right, yeah. Because if it was not a member of these, if it hadn't been assigned yet, no. So now we can evaluate clauses. We'll evaluate formulas by taking a formula in an assignment and returning a ternary. And a formula evaluates to true if every clause in the formula evaluates to true. And a formula evaluates to false if just one of the clauses in the formula evaluates to false. And it evaluates to undefined otherwise.
One of them evaluates undefined.
If it doesn't evaluate to true and it doesn't evaluate to false, then it's undefined. It could be multiple clauses could evaluate to undefined and still. But yeah.
Oh, if one of them is false and some are undefined.
If just one of them is false, it evaluates to false, right? So next I'm going to define what it means for a clause to be redundant with respect to a formula. So we say two formulas, F1 and F2, are logically equivalent if they have the same set of satisfying assignments. And we say two formulas are satisfiability equivalent if they're either both satisfiable or both unsatisfiable. So in the second case, for two formulas that are satisfiability equivalent, they may be satisfied by different sets of assignments on the common variables, but still are equivalent with our respect. It just can't be that one of them is satisfiable and one of them is unsatisfiable. And we say a clause is redundant with respect to a formula if when you conjoin the clause with the formula, its satisfiability equivalent to the original formula. So in other words, adding the clause to the formula doesn't change the satisfiability of the formula. And there are a bunch of different definitions of redundant in a bunch of different contexts, and this is just the one that we've chosen for this context. So now I'll have a little example about redundancy. So here I have a formula on the left, and it's consists of the clause 1, 2, the clause 2, 3, and the clause -2, -3. And on the right, I've enumerated all the assignments for the variables 1, 2, and 3. And then on the right of the dividing line, you can see whether or not there's a solution for the formula, whether or not each assignment is a solution for the formula. So an X indicates that that assignment is not a solution for the formula. So here, this formula can be satisfied by 3 different assignments. So now given the clause C1, which is the clause 1, -3, if I conjoin that with the formula F, then I see that I have the same set of satisfying assignments. So these two formulas are logically equivalent. And C1 is also redundant with respect to F. And next, given the clause C2, which is -1, 3, we've eliminated, if I conjoin that with the formula F, then we've eliminated one of our solutions. But it's still satisfiability equivalent to the formula F because it's still a satisfiable formula. And so this C2 is also redundant with respect to F. So now I want to talk about a couple ways to establish the redundancy property. So one way to do that is by using unit propagation, which is one of the basic SAT solving inference techniques. So first we need, before we can establish unit propagation, we define what it means to have a unit clause. So we say a clause is unit with respect, a clause in a formula is unit with respect to an assignment if all the literals in the clause evaluate to false, except for one literal which evaluates to undefined under that assignment. So given the formula on the right and the assignment on the bottom, which is 1, negative 2, then in the red box you can see that this clause is unit because all the literals are false except for 1, which is undefined. And in this case, we can extend our assignment with the unit literal, which is the literal 4 in this case. So unit propagation then repeatedly extends an assignment based on inferences from the formula. And it does that until there are no more unit clauses. So here we can extend the assignment with 4, and we get another unit clause, which gives us the unit literal 3. We'll extend the assignment with the unit literal 3. And now we've falsified one of the clauses in the formula. And when this happens, when unit propagation falsifies a clause, we say that it generates a conflict. So now that we've defined unit propagation, we'll define our first redundancy property. So we say a clause has the reverse unit propagation, or RUP redundancy property with respect to a formula, if unit propagation on the negation of the clause results in a conflict. And that statement's a little strange, so let me say it another way. We want to take the assignment that falsifies the clause and then show that that assignment will generate a conflict for the formula. So in other words, if there's a solution for the formula, it'll still be a solution for the clause we're trying to establish as redundant. So below that, I've got some ACL2 code, and I know not everybody is used to reading things in kind of a prefix format. So I have some notes off to the right side in all these cases. But this is essentially a way of establishing a function called RUP, which, given a formula and a clause, first gets a falsifying assignment by calling negate clause to get the assignment A, then performing unit propagation on the assignment A to get a new assignment, UP-A. We then evaluate our formula F with respect to this new assignment and to obtain a ternary value, and then check to see if that ternary value is false or if it's generated a conflict. So given a formula and a clause, we can establish either T or nil whether or not this clause is redundant or has the RUP property, RUP redundancy property. Another way to establish redundancy is by using resolution, and this is part of the resolution proofs I was mentioning earlier. So given two clauses with a positive version of the literal and a negative version of the literal in the other clause, we can create either a new clause or a tautology by taking a union of all of the, removing the literal that we're resolving on and taking a union of all the other literals. So here, given the two clauses above, we've constructed a new clause 2, negative 3, negative 4. And this clause is implied by the two clauses above. So this is how we represent it in our model. And notice I take two clauses and a literal on which we're going to resolve. And so in some definitions of resolution, you just take two clauses and you get a new clause back or something like that. But here we're a little bit more explicit. We give the actual literal to our function that we're going to perform resolution on. And again, the result of this is called a resolvent. And the resolvent can either be a clause or a tautology in our model. And the resolvent is logically applied, and it's redundant with respect to two clauses that are in a formula. So now we can combine resolution and reverse unit propagation to obtain the property that I'll be spending the rest of the talk talking about. So this is the resolution asymmetric tautology redundancy property, or RAT property. So we say a clause has RAT property with respect to a formula if the clause had the RUP property, or there exists a literal L in the clause such that all the non-tautological resolvents with all clauses in F have the RUP property. So that's another kind of a bit of a mouthful. So let me show you with pictures how we establish whether a clause has RAT or not. So given a formula on the left, and the blue boxes are clauses in that formula, and a potential RAT clause on the right, we first construct all the resolvents with that clause and clauses in the formula. Then for each of the resolvents, we establish whether they have the RUP property or whether they're a tautology. And if each of the resolvents have the RUP property or they're a tautology, then we say that the clause has the RAT property. And so you may ask, why do we need this RAT property? Why can't we just continue to use resolution or reverse unit propagation to establish our proofs? Well, it's because the RAT property is much stronger than the RUP property. So on the left, I have the RUP property, which can be used to express techniques such as resolution, CDCL learning in SAT solvers, unit propagation, subsumption. But all of these techniques only preserve logical equivalence. But there are some techniques out there that only preserve satisfiability equivalence, but not logical equivalence. And so on the right, block clause addition, bounded variable addition, extended resolution, extended learning, all these techniques preserve satisfiability equivalence, but not logical equivalence. And they all have the RAT property, but not the RUP property. So now I'm going to show you, and this is probably the most code I'll show in the whole talk. So now I'm going to show you how we compute our RAT property in ACL2. So first, we end up, because all we have is recursion, we end up immediately dispatching to a helper function. But before we do that, we copy our formula f so that we have something to recur over in the next function. So given a formula, clause, and a literal, we first copy the formula, and then we dispatch to the helper. Right.
It's just another pointer to the same structure that can't be mutated because this is all functional.
Right. Yeah, the copy costs nothing, and it just shares a pointer. So now, in the helper function, we're given a clause list now that we're going to recur over, a formula, a clause, and a literal. And if we're at the end of this clause list, so the clause list is our kind of working thing that we're checking through, and we're checking that everything in the clause list has certain properties. So if we're at the end of the clause list, then we'll return T, which signals success for us. Then we look at the first element of the clause list, which is a clause, and we ask if there's even a literal on which we can resolve. And if there's no resolving literal, then we'll just continue going through the clause list and we'll recur. Else, we'll compute the resolvent, and here we label it R, and then ask if that resolvent is a tautology. And if it's a tautology, then we'll recur and continue through the clause list. If not, we'll check it to see if it has the property, the RUP property. And if it does, we recur, and else we fail. And so this is the exact same kind of procedure I showed you a couple slides ago with pictures. So now I'm going to talk about how redundant clauses can be used to construct proofs. And I'll give an overview of a few different types of proofs. So we say a proof trace is a sequence of clauses that are redundant with respect to a working formula. And so I've got working in quotes there because we're going to build a new formula at every step. So on the right I have a formula with 4 clauses represented by the blue boxes. And on the right I have a proof, which is 3 red circles. So I want to take the first clause in the proof and check to see if it's redundant with respect to the original formula. And so here I establish that it's satisfiability equivalent with the original formula. And now for the next clause in the proof, I just established that it's redundant with the previous formula that we constructed. And I continue to do this until I've reached the end of the proof. And so now through transitivity, I've established that the formula on the right is satisfiability equivalent to the formula on the left, on the far left. And a refutation, then, is a proof trace that contains an unsatisfiable empty clause. So here, now the formula on the right, the last clause in the proof is the empty clause, which can't be satisfied. And since that clause is unsatisfiable, the formula is unsatisfiable, and its satisfiability equivalent to the original formula, and we've established the original formula was unsatisfiable. So this is just a refresher of some of the proof properties. I'm now going to show you resolution proofs, clausal proofs, and our RUP proofs, kind of pictorially how to check each of these proof types. And so you can kind of look for these properties as we go along. So first, a resolution proof has a lot of information in it, and it's one of the reasons they're so large. So here we have every clause represented by a blue box, every clause in the original formula represented by a blue box, and all of the proof clauses are represented by red circles. And here each of them has a label associated with it so that we can refer back to a specific clause. So in order to check this proof, we take the first clause in the proof and establish that it's redundant. And we do that through a series of resolution steps. And so here the clauses 3, 6, and 8 were all used to establish the redundancy of the new clause 9. And then we continue to do this for each clause in the proof until we reach the empty clause. And so these can be this proof style can be checked very efficiently, but the problem with it is that as you see, there's a lot of information encoded in this proof here. Every resolution step is encoded. Everything has a unique identifier, and these proofs are very. It's hard for a solver to omit all of these different steps when it's trying to actually solve the satisfiability of the formula. So another proof type is the RUP proof type. And so here, I have the formula on the left again, and the proof on the bottom left. And notice now that none of the arrows are there at the beginning. There's no information about the arrows, or which clauses are used to establish the redundancy of other clauses. And none of the clauses are labeled anymore. None of that information is necessary. Because at every step, we take a clause from the proof, and we use unit propagation to establish whether or not it's redundant. And so here, there's some amount of search that needs to take place for every clause we establish as redundant. But as soon as we establish a clause as redundant, we forget all of the relationships that establish its redundancy. So these can be very compact, but they also require some amount of search, and so they can be very slow. And finally, this is what our RAT proof format looks like. So on the left, I have the formula again, and on the bottom left, I have our proof. And the green triangle represents a clause that has the RAT property, but not the RUP property. So to check this proof, we first check to see if this clause has the RUP property, and it doesn't. So then we check it for the RAT property. We construct all the non-tautological resolvents, and then we ask if each of them has the RUP property. These are then, if each of them does, then the clause has the RAT property and it's redundant, and we throw these kind of temporary clauses away. And then we go on to establish the next two clauses with our RUP property, and we complete the proof. So now I'm going to show you how we modeled our proof checker in ACL2. So given that we've defined the RUP property already, and we've defined the RAT property, we can say what it means to verify a clause in our proof. So we say a clause, given a clause in a formula, the clause has been verified as being redundant if it has the RUP property or it has the RAT property. Next, we verify a proof or a proof trace by checking that each clause in the proof has been verified. And so we do that by first checking if we're at the end of the proof trace. If we are, we return T, which signals success. Else we verify the first clause in the proof trace, and then we verify the rest of the proof with an extended formula. We model refutations by saying that any clause list that's been verified is a proof trace. And proof traces that contain the empty clause are refutations. So then we can specify what what a proof checker should do in ACL2. And we do that by first establishing a quantification predicate. So here at the top, I establish so ACL2 doesn't have native support for quantification in its logic. So we do that through having skolemized functions in a different way. So here I'm establishing you can read it almost like you would if it were part of the logic. It says that there exists an A such that A is an assignment and A satisfies the formula. So in other words, there exists a solution for this formula, for a given formula. And our main theorem then states that given a formula and a refutation for that formula that's been verified by our proof checker, then there does not exist a solution for the formula. So in other words, the formula is unsatisfiable. And so this is the theorem that we were able to prove in ACL2 about the code that I've shown you up to this point. So now I'm going to give you a little bit of a sketch of what that proof is like, and it's a yeah.
Can you go back to the definition?
Yeah.
What if there does exist a solution?
If there exists a solution for the formula, then either we wouldn't be able to verify the refutation, so if there exists a solution for the formula, in the bottom part would become false, which would then if there exists a solution for the formula, then we shouldn't be able to verify the refutation, and the first part of the implies would become false, and so the whole theorem would become true.
I guess that theorem doesn't apply. Yeah, but what if there's a
It just has a false hypothesis. That's
Yeah.
all.
Sorry?
It just has a false left-hand side. That's all. The refutation can't be basically recognized, and therefore the theorem in fact is true.
Oh, there could be a bug in the definition of refutation.
Yes, that's true. So then back up one slide.
Yep.
And then you have to decide whether that is an okay definition of refutation. That is a proof trace, and that in the proof trace you'll discover, remember, every element of proof trace has been shown to be redundant with a formula, even if the empty clause is prior to the end of the proof trace. It's just that it was able to establish it at some point.
All right, yeah. It's okay.
So let me give a very brief sketch of what the proof of our main theorem looks like. So the theorem stated that if we had a formula and a refutation, then there does not exist a solution for the formula. So instead we can prove the contrapositive. We say if there exists a solution for the formula, then we should not be able to verify our refutation. We next prove that if the empty clause cannot be redundant if there is a solution for the formula. So given a solution, we shouldn't be able to establish the empty clause is redundant. Next, we show that every clause in the refutation is redundant. And this gives us a contradiction with the first 2 points. And we prove something like this using kind of our only, well, not our only, but one of our main methods available to us in ACL2, which is structural induction. To prove 3, we end up showing that clauses with the RUP property are redundant, and clauses with the RAT property are redundant. And this is proven using a case split on the evaluation of this hypothetical existing solution with respect to the clause we're trying to establish as being redundant. So remember, from 1, we have this kind of hypothetical solution. So if the clause we're trying to establish is redundant, if that evaluates to true under the existing solution, then we say it's a solution for the clause as well, and we can admit it as being redundant. If the clause we're trying to establish as redundant is undefined with respect to the existing solution, we can modify the existing solution by taking one of the undefined literals and adding it onto the solution. And finally, if the clause we're trying to establish as redundant evaluates to false under the existing solution, then we need to take some we need to take some part of the solution and flip one of the assignments in that solution so that this clause now evaluates to true. And the problem with that, and so that's probably one of the trickier parts of the proof, is knowing which literal we need to flip so that we don't falsify any of the clauses of the original formula. So that's a bit of a sketch. The full proof is in our code, which is online, or you can also read the paper for a more kind of detailed description of the proof.
So I guess in this part, you're basically proving that RUP actually does preserve satisfiability.
That's right. Right. And so the reason that this proof is a little bit more difficult than, say, proofs of so I've completed proofs of a verified RUP proof checker as well. But the reason this one's different is that in the RUP proof checker, all you have to do is show logical equivalence. You just take the existing solution and say that it must be continue to be a solution, because they have the same set of solutions if they're logically equivalent. But the RAT property is much more difficult to show redundancy for, because now you have to construct a new solution. You have to just say that there is a solution, not necessarily that the same solution holds. And so you can continue to modify the solution throughout the entire proof. So what I've shown you today is our model for an unsatisfiability proof checker based on this generalized RAT redundancy property, our specification for what the proof checker should accomplish, and a proof of correctness in ACL2 that shows that our model meets our specification. And so our goal in this work and moving forward is that we want to increase the confidence not in just a solver, but all satisfiability solvers by efficiently checking proofs with a mechanically verified proof checker. And so this is some of our recent work on the subject. We have a paper that's accepted for the journal Software Testing, Verification, and Reliability, 2 published papers in the Conference on Automated Deduction and Interactive Theorem Proving, and a paper that's forthcoming in Formal Methods in Computer-Aided Design. And so I will now take any questions you have, and if you want to ask about one of these other papers, I can field questions about efficiently checking proofs or any of that kind of stuff. Thanks.